So in the last lecture we proved that a prime ramifies if and only if it divides different, and this way we get that there are only finitely many primes that ramify in any finite extension of a number field. Of course, if you take infinite extensions, you can have infinitely many primes ramifying. So this result only applies to finite extensions. Now we will look at examples from today's lecture. So we will look at special fields, we will compute various things that we saw about them. So the first thing we do is we look at quadratic extensions. So quadratic extensions of Q, and although I am saying these are special examples, there is a rich theory in each of these examples. So the theory of quadratic extensions is of rational numbers is very rich. For example, you can take imaginary quadratic extensions of Q, and even before class group was defined, Gauss associated class group to this family of quadratic extensions, and this is, we will study this briefly, and he conjectured that there are only finitely many imaginary quadratic number fields with class number 1, and in fact he wrote down a complete list of it. And this took about more than 100 years to prove. He also conjectured that if you take real quadratic extensions of Q, then there are infinitely many real quadratic extensions with class number 1, and this is still an open problem. Okay. So we will look at quadratic extensions, we will look at cubic extensions, we will look at biquadratic extensions, and we will look at cyclotomic extensions of Q. Okay. And each of this family of extensions of Q has a rich theory by itself. Okay. So K over Q quadratic extension, and we know from Galois theory that K is of the form Q square root of x for some x a non-zero rational number, and it is not a square. Okay. Why do we know that? Well, K is will be obtained by adjoining root of a square root of a quadratic polynomial, and we know how to write down roots of a quadratic polynomial. Okay. But we may assume, so if x is a by b, then q square root of x is same as q square root of b square x, right, because b square is a square. Hence, any quadratic extension of Q is of the form Q square root of m for some integer m. Furthermore, we may assume that m is square free. What does that mean? Square free means no square, a square for a bigger than 1 divides m. Another way of saying that is there is no prime p such that p square divides m. Okay. So we may of course assume that m is square free, because if m is divisible by p square, q square root of m is same as q square root of m by p. Okay. All right. So from now on, let k be equal to q square root of m, okay, for a square free integer m. Okay, so in particular m is not 0, m is not 1. All right. Because square root of 1 is plus and minus 1, and so it does not give you a quadratic extension. Okay, so our first order of business is finding what the ring of integers is. So question 1, what is OK? Right? And we may have done this when I introduced rings of integers, but it is a good idea to revisit it anyway. Okay. So square root of m belongs to OK, right, as square root of m is a root of the monic polynomial x square minus m equal to 0. Right? Recall what the definition of algebraic integers is. It has to be a root of a monic polynomial with coefficients in z. Okay? I am not asking, in the definition we did not ask that the monic polynomial should be irreducible. We did prove, however, that there will be an irreducible monic polynomial with coefficients in z, for which that algebraic integer will be a root, but that is a different thing. We just need to show that there is a monic polynomial with coefficients in z whose root is square root of m. So, this is that monic polynomial. Okay. So, hence z square root of m is contained in OK. Okay. It may or may not be equal to OK, we do not know yet. And so, what did we learn very early on in the course? How do we find the ring of integers? Well, we compute delta square 1 square root of m. What is this? This is determinant of, you take trace from k to q of 1 times 1, trace. So, we did this a long time ago, so that is why I am recalling this, 1 times square root of m, trace from k to q of square root of m times 1, trace from k to q of square root of m times square root of m. If you go back and look at your notes from the beginning of the course, this is what you will find is the definition. Okay, so what is this? This is determinant of trace of 1. This trace is always from k to q, trace from k to q of square root of m, trace from k to q of square root of m, and then trace from k to q of m. Okay. And so, if you look at what the definition of trace is, the first element is, the first entry is 2, the second entry is 0, the third entry is 0, and the last entry is 2m. And so, the determinant is 2 times m. Okay. Now, m is square free. So, the only square that divides this delta squared 1 comma square root of m is 2 square. Okay. So, hence dk, the discriminant, is either m or 4m, right. We do not know which one it is. We know that z square root of m is contained in OK, is contained in half z square root of m. So, if the first equality holds, then we are done. But what is the index of? So, if I look at this, this index is 4. Right. There are 4 elements that that give you cosets of z square root of m in this. Okay. And if you look at what they are, then 1 half 1 by square 1 by half of square root of m and 1 plus square root of m by 2 are coset representatives of z square root of m in half z square root of m. Okay. So, clearly half and half square root of m are not algebraic integers. If you haven't seen this before, take this as an exercise. Okay, it's not a difficult exercise, but mind you, you have to show that half of square root of m is not a root of any monic polynomial with coefficients in z. Okay, that's the challenge. You can't just say that it's a root of 4x square minus m and hence it's not an algebraic integer. That's not a valid argument. Okay. You have to show that there isn't any monic polynomial with coefficients in z whose root is half square root of m. Similarly for half, you have to show that there is no monic polynomial with coefficients in z whose root is half. All right. So, it all depends on whether 1 plus square root of m by 2 is a algebraic integer or not. Okay. And so, what we do is we find the minimal polynomial of this. So, find minimal polynomial of alpha over q, right. So, alpha is 1 plus square root of m by 2. So, 2 alpha is 2 alpha minus 1 square is m, and so you get 4 alpha square minus 4 alpha minus m plus 1 equals 0, and so you get alpha square minus alpha minus m minus 1 by 4 equals 0. Okay. So, the minimal polynomial of alpha over q is x squared minus x minus m minus 1 by 4. Okay. And this polynomial is in z. So, again this is a result that we proved, that the minimal polynomial of an algebraic integer has to be in zx. But so, this polynomial is in zx if and only if m minus 1 by 4 is in z, right, which is if and only if m is congruent to 1 mod 4. Okay. All right. So, in this particular case, so if m is congruent to 1 mod 4, then 1 plus square root of m by 2 is also in OK. But this thing is not in z square root of m. Okay. And so, the index of z square root of m inside this is 2. Hence, OK is z 1 plus square root of m by 2 in this particular case, right, if m is congruent to 1 mod 4. Now, if m is not congruent to 1 mod 4, so i.e. m is congruent to 2 or 3 mod 4. M cannot be congruent to 0 mod 4 because m is square free. If m is divisible by 4, then m will be divisible by 2 square, so it won't be square free. Then 1 plus square root of m by 2 is not in Z, OK. And OK is equal to Z square root of m. Okay. So, as a result, what have we proven? The ring of integers of q square root of m, this is equal to Z square root of m if m is congruent to 2 or 3 mod 4, and it is Z 1 plus square root of m by 2 if m is congruent to 1 mod 4. Okay. Furthermore, we also have computed discriminant this is equal to 4m if m is congruent to 2 or 3 mod 4, okay, and it is equal to m if m is congruent to 1 mod 4. Right. We proved a general result about discriminant, but notice that in this special case we just get it from the whatever it is. So, dk is always 0 or 1 mod 4. Right. We proved this in general. This was called Stickelberger's theorem, one of Stickelberger's theorem. Okay, so we have computed the ring of integers of this. Next, we will see how to find which primes ramify in, how primes split in a quadratic extension. So, next thing we look at is splitting of primes in K, right. So, there are three possibilities, only three possibilities, because we are in a quadratic extension. P times OK is P square. So, this is ramified primes, or it is P1 times P2. P1 is not equal to P2. So, this is split case, or it is just P. This is called the inert case. So, in this case, in the ramified case, E is 2 and F is 1. In the split case, and R is 1 as well, so R is 1. In the split case, R is 2, E and F are both 1. And the inert case, R and E are both 1 and F is equal to 2. So, if you want product of three positive integers to be 2, R times E times F equals 2. These are the only three ways this can happen. Okay. All right. So, we want to find out which primes ramify in q square root of m, right. So, P ramifies in q square root of m, which is k, if and only if P divides dk, right. So, P ramifies if and only if P divides m if M is congruent to 1 mod 4 and P divides 2M if M is congruent to 2 or 3 mod 4, right. So, in the case when M is 2 or 3 mod 4, 2 will always ramify irrespective of whether 2 divides M or not. Okay. All right. So, what about other primes? Okay. What about other primes? So, let us say P does not divide the discriminant. Okay. Then I want to find what P times OK looks like. So, this is P1 times P2, P1 not equal to P2 if x squared minus m equal to 0. So, let me write it on the next line. If x squared minus m congruent to 0, mod P has a solution. In Fp. Right? This is what we saw in a theorem that we proved about how primes split. So, this is if and only if M by P is equal to 1. This is the Legendre symbol. Okay. And P OK is prime, so i.e. P is inert if and only if M by P is equal to minus 1. Okay. So, again further specializing. So, let us say K is equal to Q square root of 2. Right. So, P is ramified if P is equal to 2. Right. What is the discriminant in this case? It is 8. P is split if 2 by P is equal to 1, i.e. P is congruent to 1 or 7 mod 8, right, and it is inert if 2 by P is equal to minus 1, i.e. if P is congruent to 5 or 3 mod 8. Okay. So, you get a complete classification of the splitting behavior just in terms of data that is within Q. Right? This thing is simply within Q. You do not need to solve any quadratic equation or anything to understand this congruence. You have a prime, this is intrinsic to Q. And although this might not seem like a big thing right now, it's actually a starting point of class field theory, for example. Okay. So, the splitting behavior of P is completely determined by data that is within P within the field Q itself. Another point to note is that of course, there are only finitely many primes that ramify. So, in this case there is only one prime that ramifies, but there are infinitely many primes that split and infinitely many primes that are inert. Okay. Let us look at another example. Let us look at let's look at k equal to q square root of 5. Okay. And so the discriminant in this case is just 5 because 5 is 1 mod 4. Right. And so P is ramified if P is equal to 5. It is split if 5 by P is 1, but you can use quadratic reciprocity gives P by 5 is 1 because 5 is 1 mod 4, and so this is P is congruent to 1 or 4 mod 5. So again you get information about splitting behavior of the prime in terms of a congruence. Okay. And of course, you can keep going. So let's look at one more example for today. K is q square root of minus 5. Maybe two more examples. In this case, dk is minus 20 because minus 5 is 3 mod 4. And so P is ramified, maybe I shouldn't write equal to, maybe is, if P is equal to 2 or 5, it's split if minus 5 by P is equal to 1. But this is same as saying that minus 1 by P and 5 by P is equal to 1, which is same as saying that minus 1 by P and P by 5 is equal to 1. And we know what happens. So, so minus 1 by P is 1 if P is congruent to 1 mod 4, and minus 1 if P is congruent to minus 1 mod 4, or let me write it as 3 mod 4, 3 mod 4, right. And I know that P by 5 is 1 if P is congruent to 1 or 4 mod 5, and minus 1 if P is congruent to 2 or 3 mod 5. Right. And so we can combine these two. Right. So if you want 1 all the time, then either both of them have to be 1 or both of them have to be minus 1. So this is P is congruent to, so if they are both 1, then 1 mod 4 and 1 mod 4 is 1 mod 20. 1 mod 4 and 4 mod 5 is 9 mod 20. But if they are both minus 1, then it's 3 mod 4 and 3 mod 5, or 3 mod 4 and 2 mod 5 is 8. Right. 3 modulo. So I'm trying to use Chinese remainder theorem. So it's 7 mod 20, right? And it's inert if minus 5 by P is equal to minus 1. So this is if and only if P is whatever the remaining classes are. So 3 mod 4 and I don't know, mod 20 11 mod 20, 13 mod 20, 17 mod 20 and 19 mod 20. Okay. Alright. So, again it is the case that there are infinitely many primes that split and infinitely many primes that are inert. Okay. So, I think that is a good point to stop today. We will continue with our study of quadratic extensions. So, we saw the splitting behavior with lots of examples. Next time we will try to study a class group of quadratic fields. So, we will not do computations of class number using Minkowski's bound. Instead, we will relate it to quadratic forms, binary quadratic forms, and we will sort of relate to rich areas. One is the study of binary quadratic forms, another is study of quadratic extensions. We will look at computations of class number using Minkowski bounds later on in the course. Thank you.